I think we should now review a subject that I love and that makes a lot of people cringe: binary. Everything comes down to these two numbers, 1 and 0. Everything in your digital life is based off of these zeros and ones. So we want to distinguish, it's really important to think about this. It's not necessarily a math exploration. A lot of people are going to be like, oh, math. Some people love math, but we're not going into this subject for the purpose of learning math. We're doing it because to be the best of the best in cybersecurity, you want to understand the language of computers. So learning binary is about understanding how computers think. When you understand how computers think, you can understand how they can be manipulated, exploited, and protected. Hopefully, you're interested in protecting, but we have to learn all these aspects in order to protect. You have to think like a criminal in order to be a non-criminal who can do a difference, make a difference. So there's a lot of ways it can help you. Understanding how data is stored and manipulated at that low level helps with reverse engineering and malware analyses. There is network packet analyses, cryptography, and you've got your operating systems, understanding how they handle data in your applications as well, software. Debugging things and detecting vulnerabilities is one of the reasons why it's super helpful. What if you want to be a security analyst and you need to look at network traffic to identify a potential attack? You might be looking at binary and hexadecimal. You're like literally investigating a crime scene and there's evidence right in front of you, available to you if you can just read it. So we think about binary, we break it down. Bi is for 2. Binary is a base 2 number system. In our everyday decimal system, we're using 10 digits instead of 2, but binary you're using 2, the 0 and the 1. So the reason why computers think in binary is because of electricity and physics. Your computer has a ton of transistors, tiny switches. Each of these transistors can be of the state on or of the state off. Now, if you dive into studying electricity, you'll understand there's area between on and off. But right now, just think in terms of binary, 0 or 1, on or off. Not a kind of on, not a maybe off, but an absolute. So you want to connect on to 1. When a transistor is on, it's represented as 1. When a transistor is off, it's represented as 0. And this happens a ton per second, on and off switching, and those patterns of ones and zeros become everything your computer's doing. So use the old light switch analogy, the simple on-off light switch. Now we have light switches that can do more than just on-off. And dive into your imagination and picture, or I'll probably have pictures on the screen right here for you to look at. Think of 8 light switches in a row. When you think of computers, the first one might be on, the second one might be off, the third one, the fourth one, the fifth one, the sixth one might be off, seventh one might be on, the eighth one might be on. So what you have with all these different settings is a unique combination. Every different combination is representative of a different value. If you had the first 3 on and the last 3 on and all the ones in the middle off, you'd have a totally different lighting pattern. And in binary, if you have 8 binary numbers in a row, different ones, zeros and ones, then you have 2 to the power of 8, which makes 256. It's not the mistake I often make, which I say 8 to the power of 2, because that's only 64. It's 2 to the power of 8. So that means you can have 256 different unique combinations with these 8 light switches with on and off. So 256 different lighting patterns, or for what we're talking about, 256 different values. That's more values than the English alphabet, way more. It's more values than the Spanish alphabet, the German alphabet, the French alphabet, the Greek, the Cyrillic, Russian, Hebrew, Arabic, Armenian, Georgian. So if you're thinking about this just in terms of words, you can create all kinds without any problem with the combination of unique values for letters. Now, when we think about these switches, these light switches, each one of the light switches is called a bit. A bit is a single binary decision, on or off, 1 or 0. 1 switch, 1 bit, 8 switches, 8 bits. So you see these 8 switches in front of you, that is 8 bits. And when you line up 8 bits, you get 2 to the 8th power possible combinations, which is 256 values out of each of these decisions. These 8 bits when you combine them. So binary is that base 2 system, and bits are the units that carry the binary state. A bit is the smallest unit of data in computing. And we don't get a lot of information if we just look at a bit by itself. That's why we make these combinations, or we lined up these 8 light switches. And we group 8 of these bits together, these 8 light switches together, because that forms what's called a byte. So a group of 8 is a byte, a group of 8 bits. And we group it that way because it's large enough to represent that 256 values. Now, if we were talking about the English language, the alphabet, we wouldn't actually need the full byte to represent every single letter in the English language, like all of them. You'd only need up to about 5 bits. You're 3 bits short of a byte. The English alphabet has 26 letters. Each bit doubles the number of possible values. 4 bits is 16 values. 5 bits is 32 values. 32 values is more than 26. So that would be enough just in the 5 bits, not even in one full byte, to assign a unique value to A through Z, with 6 unused values left over within your 5 bits. And of course, we're not distinguishing between uppercase and lowercase letters as separate, or using digits or punctuations or spaces or control characters. We're just talking about the basic English alphabet. With computers, though, we group the 8 bits for our 256 bits in 1 byte, as bits are a theoretical minimum. Bytes are a hardware convenience. Memory registers and buses and instructions are byte-oriented. And if we were to use sub-byte encodings, like 5 bits or this or that, it makes things more complicated. You've heard kilobytes, megabytes, gigabytes. It has the byte in there because these are all measurements based on bytes. A byte can represent values from 0 to 255. This is where you can get caught up sometimes in testing or just conversations if you talk about stuff like this, if you're a nerd like me, because 0 to 255 is 256 possible values because you're counting the 0. You can see already that binary is not just academic theory, useless knowledge that I'm trying to stuff into your head. If you were to take a networking course, a computer networking course, like the CompTIA Network Plus, try to get certified for that. Even if you're not trying to think about cybersecurity, you still have to understand some of this because of IP addresses and various things that are related. So if you find yourself analyzing network traffic as a cybersecurity analyst, the data packets moving across a network are structured in binary. The source and destination IP addresses are encoded in binary, and the ports being used and the protocol information. Now, I know security tools interpret this for you, but tools sometimes miss something. Or if you're doing deep forensic analyses, you want to be able to read what's actually there. So like I said earlier, if you want to be a true cybersecurity expert, you want to understand binary. You want to at least understand some of it if you just want to work in computing, though, particularly in networking or cybersecurity, regardless of how many tools you have. It will be very helpful for you. The executable files for malware are actually binary files. To understand what these binary malware files do, people who have the job of malware analysts, or perform the role in part, look at the binary structure of files to understand what they do, how they spread, and how to stop them. There are certain patterns of binary data called file signatures. You might hear them referenced as magic numbers, and they can tell you things like what type of file you're actually looking at, regardless of what that file extension claims to be. It could say .dox, .docx, but then it's not a Word file, not a Microsoft Word file, or .png or .pdf, etc., and so on. Attackers will disguise their malicious files. That's one thing in life you can count on. One of the ways they're going to do that is by changing the extension, but the binary signature can tell you the truth. Maybe you are involved in an incident response and you work with memory dumps, like LSASS.DMP as one example of a high value target. LSAS, Local Security Authority Subsystem Service, the authentication fabric of your computing system. When you're looking at those memory dumps, you might be looking at raw binary data pulled from the system's RAM, random access memory. This could contain passwords, key material, encryption keys, evidence of malicious processes. But if you don't understand binary binary. You might not be able to interpret what you're seeing. Again, that's what the tools are for. But if you can understand binary, that can help a lot. And as I talked about computer networking, IP addresses, subnet masks, not only computer networking people, but also cybersecurity people need to understand computer networking and need to understand that these IP addresses and subnet masks are actually 32-bit binary numbers that we write in what we apparently consider to be a human-friendly format. So when you understand the binary behind IP addressing, concepts like subnetting and network segmentation make a lot more sense. The way that text is stored relies on binary. You've got encoding standards like ASCII or Unicode, so that every character you're typing is converted to a binary value using these encoding standards. And this really does matter for security because attackers exploit this character encoding to bypass filters, inject malicious code, and hide data in plain sight. Now, in our everyday decimal system, 10, each position in a number represents the power of 10. The rightmost digit is the ones place, 10 to the 0 power. The next digit is the tens place, 10 to the first power, then hundreds and thousands, on we go. And binary works that way, but with powers of 2 instead of powers of 10. The rightmost digit is the ones place, 2 to the 0 power, equaling 1. Next digit is the twos place, 2 to the first power, equaling 2. 2 times 1 is 2. Then the fours place, 8, 16. Each position doubles in value as you move left. So if we think about a binary number, 1011, that is 4 bits. If we read from right to left, which is backwards if you're normally reading English, from left to right. If we read the binary number from right to left, we have 1 times 1, 1 times 2, 0 times 4, and 1 times 8. So if we add those up, 1 plus 2 plus 0 plus 8, we get 11. So then 1011 in binary equals 11 in decimal. This conversion process is really important for you to understand. If you want to calculate a subnet range or analyze a packet header, here's the problem with me. I've been around too many people from too many different cultures. I have trouble with my accents. If you want to interpret memory addresses, the skill becomes second nature with practice. And just to say, I love being around people of all different cultures. So if that's a good or a bad thing in your view, it is what it is. But it's definitely influenced the way I speak throughout my life. When I was a baby, I was born in the northern part of the U.S., but because of people I was around, I had a southern accent, so I've always been a weirdo. So it seems like this might feel scary or complicated, but like anything, it can become second nature to you. It would take practice, though. So binary is that true language of computers. But people have a hard time working with these long strings of ones and zeros, so then people created hexadecimal. And hexadecimal is a base 16 number that serves as a shorthand for binary. So you'll really see hexadecimal everywhere in security tools, from memory addresses to hash values to MAC addresses. Hexadecimal perfectly maps to binary. Every 4 bits of binary convert directly to 1 hexadecimal digit. So the translation between these two systems becomes more straightforward once you understand that relationship. For this lesson, we're just bringing to a forefront the understanding that binary exists for these various purposes, and it forms the foundation of everything computers do. When you are looking at these different security tools, these different logs, things you're going to be exposed to if you aren't already, you should keep in mind that underneath all of that, you've got ones and zeros. Binary. They're translating binary into something more readable. The binary is what's real, though. Everything is layered on top of that, translated. From these 2 digits in binary, these 2 little things, we've built everything from calculators to AI, basic text files to sophisticated malware. So understanding binary means understanding that foundation upon which all of digital security is built. I recently watched a talk from Kelsey Hightower. I strongly encourage, look him up on YouTube. He's great. He's got an HA proxy video where he talks about understanding the fundamentals. Absolutely fabulous. If it wasn't plagiarism or whatever, I would just repeat every single thing he said to you right here, right now. It's a great talk. He is very entertaining, and very knowledgeable. So you've got a short quiz and an assignment, and I'll be here in video in your next lesson, at least my voice, depending on which video it is. But good luck and enjoy and dig into binary. I plan to dig in more in this course with that later on, but right now you needed this introduction. Thank you for your time.